So I'll start with the first presentation, which is about antenna simulation with CST Studio Suite, so our SIMULIA tool for electromagnetic simulation. First question, of course, is where do we even use antennas? Well, literally everywhere. We see trends in industry and in our lives towards increased telecommunication. So 5G and 6G networks are coming. 7G research is going to start in a few years. And we see the commercialization of space, so non-terrestrial networks for satellite communication with clusters or large arrays of distributed antennas on multiple satellites. Then we have autonomous vehicles and other things, and the sensor networks, which they communicate with, smart facilities, healthcare, basically any industry or application that you can think of. Antennas are the key technology that enable communication. They are literally everywhere. Simulation, of course, is intended to help engineers confront the challenges that they are faced with in their daily lives. So those challenges are not of our making as engineers, but they come from us as well as consumers. We want, as consumers, or we need, well, we think we need new technology, not in 10 years' time, but next year, next month, tomorrow. So as a consequence, we have very short design cycles of the order of weeks or months in some cases. There's very little time to iterate, to test new prototypes. We also expect a large number of product variations to suit all our different tastes, but those variations, of course, have implications again for the design of antennas. Finally, we expect devices with more and more functionality. So standalone digital cameras, music players, those are pretty much niche items today. We want integration, but that again causes high complexity in a small package, resulting in potentially unwanted interactions, interference between systems. Again, this poses challenges for the design of the antennas in the context of their devices. So those are a few of the challenges that simulation tools today are helping the engineer to address. Now, to be used effectively, simulation must be used early in the design process. The earlier, the better. Why early? The earlier you can identify possible issues, the more time and options you have to resolve those issues, the cheaper it is to get a good design out of the door. Getting a robust working design early on, therefore, reduces the overall risk of the project and the cost, avoids delays to the whole product development cycle. Simulation is really crucial if you were to achieve this goal. Now, we spoke of the design process, and you can roughly describe it something like this. You start off with specifications. Something must be a certain size, a certain weight. It should have a certain cost and be used for a number of applications. It has to have certain characteristics in terms of performance, so frequency range, polarization, scanning ability, etc. That is turned into a design, which is in itself a complex iterative process, and that's probably the heart of most of the talks that we're talking about today. We go on to certification of the design for release on the market. And finally, of course, success. Successful design reporting of results, and going on to the next project. Now, simulation plays a central role in the design and certification stages, but we're also increasingly using simulation in the initial what-if analyses that inform our specifications, and also in reporting results. After all, pictures are worth 1,000 words, if I may use that cliche. But let's turn now to simulation solutions for antennas. And I'd like to structure my talk in 4 parts, talking first about simulation techniques, secondly, about antenna-specific simulation challenges and how we can address those, then about safety, then about antennas in and on things, bottom left, and finally about safety and certification. So let's first talk about the techniques. Now, this is a graphic that we've used for quite a few years. Let's call it an old slide, but it's still valid on the whole. We can divide the application areas for which we're designing antennas into environments by size. On the vertical axis, we have small devices or small features, or very large devices, or large antennas themselves, or something large that you want to put an antenna on. So electrical size and feature size on the vertical axis, bandwidth and resonant behavior on the horizontal axis. So from wideband, non-resonant to the left, to highly resonant or narrow band, maybe multi-band on the right. And on the whole, So to get a good initial solver choice, so because the reason that to choose a good solver for the right type of application makes your simulation speed and accuracy trade-off much better. So you can get a fast result with a good accuracy. On the whole, when we're talking about resonant antennas and smaller antennas, we're talking about using frequency domain solver approaches. Though, particularly with the advent of domain decomposition methods, the frequency domain solver, so the FEM type approaches, become much more relevant for even for larger and more wideband approaches or applications. On the whole, for non-resonant structures, a time domain approach is going to be more suitable. Generally, as we get to larger structures, we can start using specialized techniques which make use of surface meshes. So integral equation, method of moments, multi-level fast multipole approaches. If we have very large antennas or structures, we might even be able to use asymptotic methods like a shooting bouncing ray method. Now, as I said, it's a good way of making an initial choice, but there are many other things to bear in mind. Number of ports. What sort of meshing approach might I want to use? Surface or volumetric, tetrahedral or hexahedral? What boundary conditions might I want to use for some specialized applications? What material properties are supported? What HPC, high performance computing techniques are available? So there are a lot of additional things which might inform choice, but this is a good way a good place to start from. I should point out another advantage of having access to multiple solvers, or by looking at same problems with multiple solvers, is that you can kind of get a validation by comparing results from different techniques. You can validate the accuracy of your simulation. So we provide within our CST Studio Suite access to a range of simulation methods, both time domain, frequency domain, integral equation, and asymptotic, and even some additional ones like mode matching. They can use different mesh types. Those can be volumetric or surface-based. They can be divided also into full wave or ray tracing approaches. So depending on the size and the level of complexity of your model, you might choose between them. Meshing is very important. So curved or conformal meshing, that is meshing which accurately represents the geometry and the materials of the model, is crucial to get accurate results without an exploding simulation time. So all the approaches that we offer support curved or conformal meshing. Now, these can be used individually, or of course, they can be coupled to each other. So all of them can talk to all the other solvers by using bidirectional hybrid simulation approaches, where you use near or far field coupling interfaces. In addition, we would take into account circuit effects. So for example, for matching or for feed networks, we can take into account thermal and mechanical effects. For example, for thermal being something like electronic cooling. So this can be added to the electromagnetic simulation as well. We'll see a lot more detail about how all those are used during the course of the day. But let's talk about a few specific general challenges for antenna simulation. The first of those is, where do I even start where do I even find new antennas when I need to start a new design? Of course, you can scan the literature, you can use your experience, you can repurpose or update some legacy designs. But a powerful alternative is our antenna design tool, Antenna Magus, containing validated design algorithms for over 350 different types of antennas of all different shapes, sizes, and operating principles. We can use frequency specifications. So for example, here I've got 3.75 gigahertz selected. So that's a 5G band N77 frequency. We can use radiation properties if we want to. You can specify spatial limitations, which we're also using here. So we have a certain volume that's available, and keywords. So here we've selected integrated and compact. Results are grouped for you by antenna type in case you have a particular manufacturing technology in mind. So if you're making something of wires or planar, if you're looking at dielectric antennas, you can filter immediately by those. In this case, the most, and of course you get an immediate visual indication of how well the various antennas fulfill your objectives. So in this case, the first choice with a goodness factor of 1 is this cross T-shaped dielectric resonator. I've never encountered this before. I didn't know about it previously, but it looks quite interesting. So it might be worth an investigation. And that's what we're trying to do at an early design stage. We're trying to find out what types of antennas might come into question for our design problem. And then we want to quickly evaluate those alternatives so that we can shortlist the 1 or 2 or 3 most suitable candidates for our application. So here, for example, we have 9 different antennas, all of which could work. And we can, at the click of a button almost, very quickly, within a minute or two, we get some pre-calculated results, which we can compare directly with each other to evaluate the expected performance. And then we can export fully meshed, fully set up models of those for further study and further modification in CST Studio Suite. And further modification is exactly what we need to do next, because antennas are not on their own in floating in free space in ideal form. If we look at some examples of antennas in their environments, the first thing that becomes apparent is that it is in something else or on something else. The blade is under its cover. The phone antennas are, well, in the phone. The reflector is under its radome. And you can see that choosing the right solver for the different antennas now becomes a little bit more complicated, because it depends not only on their physical behavior and size, but also on their environment. Another important topic, bottom right, is that of intellectual property. So we do offer encryption for models, so a way of shielding the internal structure, or the entire structure, except for the outline of the model, but it still retains its mesh properties, its solving properties, and so on. So it can be distributed or given to a partner, which they can then use it for further simulation of that antenna in its intended application. Let's look now at multiple antennas. So if we look at the phone, we can see in fact that there are many antennas for all the different communication and navigation standards. This will be a recurring theme today. So antennas are often not used on their own. Now, antennas in close proximity to each other can couple, and they can cause interference between their systems. So for example, in this case, we have a 4G LTE antenna. It's an old phone, coupling to a digital cellular service, a DCS antenna. Now, the coupling mechanism is not necessarily simple. So here it includes interactions with other elements in the phone, like the battery, the speaker, and the connectors. So that means in order to understand the coupling between those two antennas, you actually have to include a lot of detail within the phone to properly understand how that interference is happening. Once you do simulate the entire system, you can do an RF system simulation to obtain an interference violation matrix. More about this later in one of the subsequent talks. But what that allows you to do is to understand where unacceptable performance is coming from and to design mechanisms to mitigate that interference. Of course, multiple antennas can also act in cooperation with each other. And we're often using this principle, either to put antennas in arrays. For example, in this phone, we've got 3 5G millimeter wave arrays. So it's not that old. We've built that into this concept. Or you might have a multiple input, multiple output configuration, a MIMO configuration, which the 2 LTE antennas here are doing to provide spatial diversity. Now, let's continue more with this array topic, because this has been for a while and continues to be a massive trend in antenna design. It's very important. And we in CST Studio Suite over the last almost decade now have been developing customized, well, not customized, but specific antenna array design tools. It's a challenging task. And we've broken this down into stages which are automated and highly assisted for the user. So first step would be to design an element for the array. So for example, here we've specified a frequency range, etc., a dual polarized feed, some scanning requirements. And using antenna megas, we've identified and shortlisted several attractive-looking candidates for further investigation. We then use the unit cell simulation project, part of the antenna array task, to automatically set up all the required unit cell level simulations. And then we calculate or even optimize the performance of that element for its function as part of an infinite array. So infinite array because it's a unit cell level that we're looking at this at. So we look at the active element pattern performance over the frequency range and the scan angles of interest. And then we use the array layout to multiply, to get an antenna factor or an array factor, which we then multiply by the active element pattern to get the predicted performance of the full array in post-processing. So this is really a first level design. But of course, in reality, it doesn't take into account the variation that we have in the element's behavior. So for example, we have edge or center or corner elements also non-periodic things like the radar or like calibration lights. So to predict the performance of that full array, we do a full simulation of the entire array with its housing, with other elements. This time we use the full array simulation project of the array task to set up that full model. And we can run that using some novel approaches, which we might talk about in the next presentation about arrays, but to speed things up. And what we obtain is an accurate prediction of the full array scanning performance, including finite array effects. Should mention here, again, a little bit about the solvers that are being used. So at the element design level, we're using the frequency domain solver with unit cell boundary conditions. At the finite array level, we're also using, often these days, the frequency domain solver, but in its domain decomposition method form, so the DDM frequency domain solver. Or we could use a time domain approach as well in certain cases. When we are placing antenna, so base station antennas in a network infrastructure, so we're often having multiple antennas in close proximity to each other, even at the array level. So where do you put all these? Well, they have to be in close proximity, but they will influence each other because of that proximity. And this is something that we need to understand. Now you can imagine that once you put multiple large complex antennas in a single model, the simulation of those becomes pretty complicated. And this is where our hybrid solver technology comes in very useful. So in this case, we have two arrays placed in close proximity on two parts of a mass, let's say. For each of the individual arrays, we use a time domain approach. Could also be a frequency domain approach. But we use a time domain approach, and the space between them, so the coupling between them, we are simulating using an integral equation approach. So that's kind of simulating this relatively small channel, so the local environment. And the hybrid solver provides this kind of unique combination of time and integral domain, or as we'll see, any other combination of high frequency solvers, which allows us to really accurately study the coupling between even quite complex antennas. There's a link, so we'll post this afterwards, to a talk specifically about this topic on our website. We can use this information in different ways. So for example, we could excite all the ports in both the transmit and the receive arrays to obtain a full S parameter matrix and all the embedded antenna patterns. Or the other approach is to excite all the transmitting elements simultaneously, so for a particular scan angle, and then see how the array as a whole couples to the elements in the other array. That also gives us the radiation efficiency of the array. Importantly, all of these quantities are for the array in its actual environment. That is, they include the effect of neighboring arrays and also the physical infrastructure. Now, for any antenna or combination or communication system, we're often interested in specific performance indicators, which reflect how well those antennas or systems are going to work. So post-processing is a really important way to directly obtain those KPIs, those key performance indicators. That can be different for different applications, but specifically for 5G millimeter wave antenna design, an important antenna design topic at the moment, we have some nice functionality which we've introduced, which makes the evaluation and the processing of these antennas easier. So as we said, there's some millimeter wave arrays in our phone that we showed earlier. But what we'd actually like to see is the total scan pattern, for example, or the cumulative distribution function of the EIRP, the equivalent isotropic radiated power, and then the power density on particular planes when we think about certification, which we'll talk about later. Now for this, and for some other use cases where demanding post-processing is required, we've implemented specific post-processing functionality to make your life as a user easier and to guide you through the process and do the post-processing for you. In this case, we simulate all the millimeter wave ports and then do all the rest in post-processing. You can import the codebook, which specifies all the beam configuration, and the outputs you require are calculated for you. There's a link to an example of this being used in industry at the bottom right, if you're interested. Now, a brief mention about non-parametric optimization for antennas. This is a talk, there'll be a dedicated talk for this topic in a short while, but the point is that custom antennas for compact integrated devices in particular are a difficult task for which parametric studies often aren't suitable. And we're working together with our another SIMULIA tool called Tosca on a way of implementing non-parametric optimization for electromagnetic problems. Effectively, what we're doing is defining a region which can be used for the antenna design, and then using non-parametric optimization to shape antennas for that space, so for their specific environment. This is quite a simple example shown here, a square monopole growing into this space, 75 millimeters squared roughly, to give some kind of wideband functionality. Or we could take a half a monopole, which we can then obviously mirror to form the full monopole, to give, again, a certain performance at a certain space. Now that's fine, it's just a planar monopole, you might say. However, look, we can do the same thing for an arbitrary underlying shape. And this is where this becomes really interesting. So here we have a cylindrical substrate, and we're again just specifying a sheet wrapped around the substrate and saying, please grow me an antenna or optimize me an antenna that's going to work as I expect or as I want it to, but for this particular underlying shape that I have in mind. And this could be, as I said, arbitrary. We're not confined to cylinders or spheres or anything because it's non-parametric. The interesting thing about this example at the right, oops, there you go back one, it's vanished as it goes again. The interesting about this is that we're actually using two forms of non-parametric optimizations. We're first doing a topology optimization to get the desired functionality. Then it switches over to fine-tune the geometry using shape optimization. This is a sort of a topic on its own in a way, because we can use this, well, typically we would use this to really take an existing design and then tune it that little bit further to get really high performance. So for example, here we have a shaped or a horn, which started off with an exponential profile. And through shape optimization, we can shape its profile to optimize the cross polarization better. So a lot more details to come and much more impressive examples, I think, as well, in Genesis talk, which is coming up later. Now, let's talk about the environment. Why is this so important? And here we want to talk about, firstly, antennas on things. So whether it's the human body, an aircraft, a vehicle, or antennas in things. Those could be in compact environments, imagine in your phone, or in large environments, imagine a room or a factory hall. Let's start small though. So the point here, so here we're looking at a 5G millimeter wave antenna array inside a phone, which is radiating out through the cover. And the point is that the phone and the cover, so the environment of the antenna, becomes a part of the radiating structure. It influences the radiation. So we have what we might intend with the naked or the standalone antenna radiating out to the front. However, we have some reflection back from the cover or the radome. We have potentially some waves being guided in the dielectrics and re-radiating at the end of phones. So all these things become a part of the overall radiating structure. We could call it part of the larger antenna, and they have to be taken into account during the design. We also typically, when we're placing antennas, need to protect them from the elements. So from rain or snow, hail, temperature, even lightning. And as such, the shaping of that antenna, or at least of the cover, its structural behavior or characteristics, its aerodynamic properties become important, and they act as a constraint for the antenna design. They influence the design of the antenna, and you might have to do a co-design of that radome shape and the antenna itself. So here, again, two examples. One of them is splash plate reflector antenna for satellite communications within a UAV. So that antenna is mounted on the front top of a UAV, unmanned aerial vehicle. It's on a gimbal, which allows it to rotate. And so even if that radome is well designed, it could still influence the antenna pattern when we scan to high angles. Now we can simulate the antenna with the radome using an integral equation solver approach. And with those results, decide on whether that radome antenna combination is going to work, or whether we might want to redesign one or other of the elements. Same approach on the right for an automotive radar behind the bumper of a car. That's now at a much higher frequency. So on the left, we were using integral equation solver. On the right, we're at 77 gigahertz. That becomes a huge problem electromagnetically. So here we're actually using an asymptotic solver approach to calculate its install performance and its influence on the radar system. Now, the point is that previously we were installing antennas in things. When we put them on things, it also changes their performance. This example will be described in much more detail by Tobias later on. But here we have a VHF antenna, which needs to be placed on the tail fin of this helicopter. I know typically they're under, but let's put it on the tail fin of the antenna of the helicopter. But where do we put it? Because so the point is that we need to understand how the positioning influences the performance of the antenna. How does it change the nominal, so nominal meaning on a flat ground plane antenna performance? Please note also that in this case, we're using the time domain approach because it's a relatively small problem. Even though it's a helicopter at 127.5 megahertz, this isn't an electrically large problem, or not very large. So the most efficient approach here was the time domain approach. Note also how that pattern changes is different depending on exactly where you put it. We're not showing here, but we can also take into account a parameter sweep, for example, of rotor positions. So that could reveal a range of variation for each of these patterns as well. So first, we understand that placing it at all affects performance. But now we need to understand how precise positioning affects performance. So you might want to move an antenna back or forth on the fuselage to reduce interference to another system, to another system. So for example, here, we might want to move it further back so that it's not so close to some of the other antennas. But as you move it closer to the tail fin, you have the red curve that results. So you introduce a null in the horizontal radiation pattern at the top right. And also the vertical radiation pattern has more nulls and is maybe a less good positioning for the antenna to achieve a nice spherical communication. But and of course, we even have the matching bandwidth, which reduces because we're moving the antenna closer to the tail fin. So the point is understanding how the position of an antenna in its larger environment influences its performance allows you to make the decisions about how to place it. Of course, there's one more thing, minor technicality. So typically we don't have a single antenna in this space or on the vehicle. We've got a range of antennas for various communication and navigation functions, working across a range of frequencies. And these can interfere with each other, both in, but also out of the operating bands. So we have to be able to identify the potential critical issues and mitigate against them. So for example, by changing the position. And we've got a nice way of doing this. First, by calculating the coupling matrix. So running a simulation, broadband of all the antennas to get the S parameters of the coupling between them all. Then defining the radio frequency systems, not only of other antennas, but other systems that might radiate as well, unintentionally. And those can be combined to then give you the interference matrix. There are two arrows as well. So that's using our interference task. The interference matrix gives you a nice visual form or visual representation, which transmit-receive combinations are okay, green ones, maybe not okay, the yellow ones, or really not okay, you should do something about this. Those are the red ones. And by okay, we're always talking about meeting the electromagnetic interference limits, so the EMI limits. And this will be talked about, as I said, a lot more by Tobias. So those are antennas in large environment. Now we get to a very large environment. And here again, this is strictly speaking, not an antenna design problem, but it influences antenna design. So we should talk about it. So in an environment like this, an aircraft hangar with some aircraft and various other bits of equipment in it, we need to perhaps understand how many antennas are needed to provide adequate coverage. Where should they be positioned? What types of antennas should they be? What should their scanning range be, et cetera, et cetera. So we can run simulations using a ray tracing approach, so our shooting bouncing ray method, to, for example, look at what happens if I place transmitter 1 at this position in the ceiling of the antenna. I get a slight shadowing, you can see of the aircraft, but I get good reception or good coverage in one half of my hangar. Transmitter 3 at the far end gives me another coverage in some areas, but not in others. I can start combining them, and by the time I've got 3 transmitters, I'm getting reasonable coverage throughout. Now, the point is that to understand this, to kind of investigate this in a complex environment, such as in an industrial environment like this aircraft hangar, you need to have an accurate 3D model of not only the room itself, so the building, but the things that are inside it, which can be quite challenging. And then also the antenna patterns themselves. This is something that we're dealing with more and more within our CST Studio Suite, but also as an organization, because we have links to all the modeling tools that our sister or brother or sibling brands like CATIA and SolidWorks are providing. In addition to coverage, we might want to look a bit more closely. So how does energy get to from one antenna, so from our transmitter to another antenna that might be moving through the environment? And we can use a combination of solvers, so time domain solvers, for example, to calculate how a single antenna radiates. Then we use the asymptotic solver to calculate how the energy spreads through our environment. And then we use our system assembly modeling technique, which Tobias again will talk about later, to do a parameter sweep of the receiver as it moves along a mission path through the environment. And we can calculate how the path loss changes. So whether from the transmitter to two receivers, in this case, a front and a back one on our little vehicle, whether that path loss will be too strong or whether we are able to communicate throughout the mission with this thing. So this is for one transmitter communicating with two receivers, but we could do this for a range of combinations. So here we have 3 transmitter positions communicating with those 2 receivers, one on each on the back and front of the vehicle. So 6 combinations overall, and we get a best case for this mission. Okay, so at all points, basically throughout the mission, some antenna should be able to communicate, except we still see some nulls. So we still see some weak points at certain locations as this AGV, this autonomous guided vehicle, is moving through its environment. So we might need to either improve the network by using more antennas or different antennas, or we might have to use better receiving antennas on our vehicle to ensure a stronger communication. The point is that by running these sorts of simulations, we can understand the problem and start devising ways of solving it. So the last topic, and I won't spend that long on this one, is the effect of the human body on antennas, or the effect of antennas on the human body. It's kind of a two-way problem. So the key thing that we're considering here is safety. We're certifying antennas for safe operations in the vicinity of people, which is in all of our interests, since all of us are often using our phones right next to our heads. Now, obviously, fields from antennas in our phones don't only radiate away from our heads or around our heads, they quite happily radiate into our heads, where they are absorbed and where they can cause heating of the tissue. And what the equipment manufacturer has to ensure is that heating is not above certain limits, so that it isn't dangerous. So for compliance, to be able to sell your phone on the market, the power loss density over a certain tissue mass, typically a gram or 10 grams, has to be below legal limits. The specific absorption rate is the quantity that is of interest here. This is for lower frequencies, so below 6 gigahertz. At higher frequencies, things change slightly because the fields don't really penetrate into the human tissue very far. They only affect the outside layer of the body. It's still important. There are still exposure limits which have to be adhered to. But for this reason, so for example, at millimeter wave 5G, we have to evaluate the field on a plane a certain distance from the phone. So for example, 2 centimeters from the phone on a surface, what is the maximum field? Now, these standards are obviously still in development, and they will be continued to develop as new operating frequencies are supported. And we, as an organization, are actively participating in the development of those standards. So our simulation technology is always up to date as far as evaluating these quantities is concerned. Right. And if you want more information, this is a very interesting topic. There are some webinars and some other presentations that you can watch on our website. We can post the links afterwards. Now, limits also apply for not only for users of phones or other worn devices, for example, but also of people or workers that are exposed to electric fields in areas where they are pursuing their occupation. So, for example, if I'm working on a ship and there's a high frequency monopole operating at some frequency, what areas should the crew avoid? Well, again, we can simulate this, and we can nicely illustrate or predict and illustrate the safe zones where crew shouldn't be by using these sort of three-dimensional isosurfaces at specific field values. At higher frequencies as well, let's say I'm a base station antenna maintenance person, engineer, and you have to go up and do some work on the top of the tower. And another base station far away is still radiating or trying to, are you going to be exposed to fields from that base station? Are those exposure limits being adhered to? This is a much larger problem, which is again why we use a sort of a hybrid approach here. So we use an asymptotic solver to calculate the fields on a box surrounding where the work is going to be. So the fields from a distance impinge on the box. We set up an equivalent near field source, and then we calculate how that near field source radiates inward onto a person, so onto the human body model, and can again calculate the specific absorption rate and so on. Now, the last point that we need to make here, which is very important, is that you can't do any of these exposure or these certification studies, perhaps with the exception of the 5G millimeter wave surface type analyses. But all these other things rely on having good quality human body model representations. And we have a project which is developing human body models, high resolution models. They can be CAD based or voxel based. So CAD means actually having solids that are meshed. Voxels meaning that you just divide your space into small cubes with a particular material property, so voxels. So we have voxel and CAD-based human models. They're high resolution. They cover a wide range of a population, so both in terms of gender, in terms of shape and size, and of course in terms of age, because age affects the properties of the tissue type. So we have a number of tissue human tissue types which have age-dependent material properties. And of course, as we can see at the top right, these are posable. So we want to consider not only straight up standing humans, but humans that are sitting or moving or lying down, or that are in the position that they might actually be in when they're exposed to electromagnetic fields. And using all these human body models, we can perform a range of electromagnetic exposure analyses suitable for certification. Finally, antennas are not just about the electromagnetics, and it's not something that we're talking about too much today. We're focusing really on electromagnetics today, but we need to potentially have to decide, if I drop my phone, is a metal frame or a plastic frame going to be better to make sure it doesn't break? And how does that affect my antenna design? If I place an antenna in the car, the automotive, if I position that in a certain place in the bumper, what's going to be the impact when I drive through the rain or through the mud? Is that area going to get covered by mud and prevent the operation of the antenna? So linking electromagnetic design of the antenna to structural, to computational fluid dynamic design, taking these things, seeing these things in combination is really important to designing antennas that work well electromagnetically, but that also are right for the job that they're meant to do in the environment or in the device that they're meant to enable. So that brings me then a few minutes late, but I think we still in relatively in good time to my conclusion. And really the short thing, or the short conclusion, is that without antennas, we don't have any connections. So they're really a fundamental technology for our modern lives. And they're used in all industries, in many applications. Anything that's smart or connected has to have antennas. With our tools in CST Studio Suite, and also our partner brands, we are providing a range of solutions for various aspects of antenna design. So, it's substantially a multi-scale problem for antenna design. So we've got antennas in and on things. So we have a range of solvers that give you options at all stages of the design and the analysis process across all different types of antennas in all different types of environments. And of course, we don't work in isolation as antenna engineers. We're given specifications. We have products and designers providing us with we have designers providing us with products and environments in which our antennas have to function. And we need those to be correctly represented if we want to do relevant design work. And so using simulation in the context of the larger portfolio of tools that we as a brand and as an organization provide and can combine with each other using our 3D experience platform gives us a lot of potential for doing our job as M10 engineers more effectively. So I think with that, I will wrap up.